In this situation, we have a pipe, a cylindrical container, lying on its side in a horizontal position, like I've drawn, and we fill it up halfway with water. Something like that. So the bottom half here has water in it, and the top half has some unknown gas. And we know the radius is 1.1 meters. And what we want to do is we've got a tricky setup here with a little laser that can run along the side of the vessel and point in. So let me draw those situations. I'm going to stop the video here and draw those. Okay, here are some cross sections of the pipe, and let's take a look. So if our little laser is located right here, and it shines its light towards the center of the pipe, because of the difference in index of refraction, there's going to be a change in direction, and it's going to take off in that direction, right? It's going to bend away from the normal. And if we continue to move our little laser out a little further, so that S is still less than 1.09 meters, then eventually we're going to get to that point where the light just barely skims the surface, just above the surface. And when S is equal to 1.09 meters, that's where it actually goes right along the surface. And anything more than that we get total internal reflection. In part A, we're looking for the index of refraction of the gas. So let's go ahead and find that. First thing we have to do is realize what they give us arc length, and we really want angle, right? So we have to go back to our definition of radians and realize that the radius times the angle in radians is equal to the arc length, and that's only if theta is in radians. So that means that theta is the arc length over the radius, and they tell us what the critical angle is. It's an arc length of 1.09 meters over a radius of 1.1 meters, and I get 0.991 radians. So now we can use our law of refraction. N1 sine theta 1 equals N2 sine theta 2. And what we have here is N for the water times the sine of theta critical is equal to N for the gas times the sine of 90 degrees. Because what we're interested in is this situation right here. Here's our normal to the surface. This is theta critical, and that's 90 degrees on the other side. And so of course that's 1, and we get the index of refraction for our gas, 1.333 times the sine of 0.991 radians, or 56.8 degrees. So make sure your calculator's in the right mode, and I get 1.115 for my index of refraction. Now we can switch over and look at part B, where they're looking for the time it takes the light to travel those two distances. So let's take a look at that. Of course, we know that the time is going to be the distance over the rate. And so we really have two different cases here. In the first case, S is less than 1.09 meters. And in the second case, S is greater than 1.09 meters. And when S is less than 1.09 meters, then part of the distance is in, let's just take a look here. When S is less than 1.09 meters, part of the distance, let's see, I'll use green. Part of the distance, that's this green case here, part of it is in water and part of it is in the gas. So half the distance is in water, half the distance is in the gas. So 1.1 meters is the distance in the gas, and it also travels 1.1 meters in the water. So it travels, the light travels a total distance of 2.2 meters, half of it in the water, half of it in the gas. So the time is going to equal the distance, 1.1 meters, over the speed of light, in the gas, plus 1.1 meters over the speed of light in water. And when S is greater than 1.9 meters, then the entire distance is in water. So that means and that distance is 2.2 meters. So the time is going to equal 2.2 meters over the speed of light in water. And remember that the index of refraction is defined as the speed of light in a vacuum over the speed of light in that medium. So the velocity is c over n. And we know what c is. It's 3 times 10 to the 8th meters per second. So let me, first I'll do s greater than 1.09 meters. I get the time is 2.2 over 3 times 10 to the 8th meters per second over 1.333, and I got 9.775 times 10 to the minus 9 seconds, or 9.775 nanoseconds. And for S less than 1.09, then we have our two different that's this case here. We have 1.1 meters over 3 times 10 to the 8th over 1.115 plus 1.1 meters over 3 times 10 to the 8th over 1.333. And what do I get? I get 4.088 plus 4.888 times 10 to the minus 9 seconds, which is 8.976 nanoseconds. So in this problem, you're really interested in how the light changes, what happens with the refraction of light at that interface. And so we're given a critical angle, and it's just a matter of finding the index of refraction for the gas. And then for the time, the key equation is that the velocity of light in that material is the speed of light in a vacuum divided by the index of refraction for the material.